Hall effect is an important phenomenon in magnetism that allows us to determine two things. It allows us to determine whether the charge carriers in a conductor are positively or negatively charged, and it also allows us to measure the number of charge carriers per unit volume of the conductor. We've seen that before, number of charge carriers per unit volume, when we were talking about current and current density. I told you that was something that was specific to the type of material. So this Hall effect is how that number is measured or calculated. And so to understand the Hall effect, I have a little diagram here. This orange rectangle represents a conductor that's placed in a magnetic field. Those X's represent the magnetic field, showing that it's pointed inward into the screen. And so basically what we're going to do is we're going to send a current through this conductor. Our current's going downward. Now let's say that the charge carriers are positive. So in other words, those charge carriers, our little positive charges, would be moving downward in this conductor. Now we know that when a charged particle moves in a magnetic field, it can experience a magnetic force, and I can use the right-hand rule to determine the direction of that force. In this case, my thumb would point downward, my first finger would point in, and I would find that my 3 fingers would point to the right. So the magnetic force experienced by this positive charge would be pointed to the right. And that would cause the positive charge to kind of move in an arc like this and stop once it gets to the right side of this conductor. And then we'd have more positive charges doing the same thing, so that eventually the right-hand side of this conductor would become positively charged. Now that's the case if my charge carriers are positive. But what if my charge carriers are negative? Well, let's see what would happen in that case. Let's erase all of these so that I don't get confused. And we know that negative charges move in the opposite direction of positive charges. So I'd have a negative charge moving upward. Because again, we know that current is the direction positive charges move. So if I have a negative charge moving upward, and again I use the right-hand rule, I'd find that that negative charge that moves upward would also experience a magnetic force pointed to the right. Because remember, negative charges do the opposite of what the right-hand rule tells you. So if that would be the case, then my negative charge would curve over, and eventually the right-hand side of my conductor would end up being negative. So this person who started this experiment, Edwin Hall, he said, well, let's see what the right-hand side of my conductor ends up being. And after repeating this experiment over and over again, he found that the right-hand side would end up being negative, not positive. And so he's the first person to say, hey, in a conductor, the charge carriers must be negatively charged, not positively charged, as we had previously assumed. Here's another depiction of that same phenomenon. So again, if I have negative charge carriers moving up from the bottom, opposite the direction of current, I find that the right-hand side of my conductor is negative and the left-hand side of my conductor is positive. If I end up with positive charge conductors moving in that same direction as current, the right-hand side would be positive and the left-hand side would be negative. And that just isn't the case. That was not found to be experimentally true. Now, that took care of the first part, talking about how we know that the charge carriers in a conductor are negative. Again, remember, this is well before the discovery of an electron. So this was the first time they realized that the things moving were negatively charged, but they didn't know what those things moving were. Now, I also mentioned that one of the benefits to this experiment was being able to come up with the number of charge carriers per unit volume. To figure that out, we're going to have to do a little bit of math and some measurements. For starters, we're going to measure the potential difference between the left and the right side of my conductor. We see that the left side is inherently positive, and so it's a higher electric potential. And the right side is inherently negative from all of those electrons being accumulated there, and so it's at a lower electric potential. Now, we know that electric potential has a relationship with electric field. Specifically, the electric potential can be equal to the electric field times the distance between the two when the electric field is constant, which would be our case here because we have two charges accumulating on opposite sides, so it almost like it acts like two parallel plates. According to my diagram that I'm using right here, the distance between the two sides is E. So I'm going to say that the potential difference equals E times D. Now, if I've left the current on for some measurable amount of time, it would eventually get to the point where there's a whole bunch of electrons on the right-hand side and a whole bunch of positive charge on the left-hand side. And so we have an electric field set up in between these two, and that's my electric field that's marked up at the top here. Well, if I have a negative charge that's passing through, it would experience a magnetic force to the right and an electric force to the left. And eventually, once equilibrium is reached, those two forces would be equal in magnitude. Similar to what we talked about with crossed fields. Fe would equal Fb. And so that tells me that Q times E is equal to QVB sine theta. And of course, we're only setting them equal in magnitude because we know that they'd be opposite in direction. Just as before, our sine of theta is equal to 1 because the angle between my velocity and magnetic field vectors is 90 degrees. And really, when I'm talking about velocity here, I'm focusing mostly on the drift velocity that these electrons would have as they travel through my conductor. Going back to that idea of drift velocity, that's back from chapter 26 when we learned about it. Drift velocity was kind of described as being the current density divided by the number of charge carriers per unit volume times the charge on a single charge carrier, E. Or another way of writing that would be the current divided by NE times the area. And in this case, we're talking about a cross-sectional area that this current travels through. Now, using this equation, setting my two forces equal to each other, I can cancel those two Q's out, and I get that that drift velocity is equal to E over B. So I can set these equations equal. Now, what I'm really trying to do is find an expression for the number of charge carriers per unit volume. That's what that little n represents. So I'm going to solve this expression that I have here for n. I get that n is equal to I times B, or the current times the magnetic field, divided by the charge on an electron times the electric field times the area. Again, cross-sectional area. Now, I would know what the current is that I'm sending through my object. That's something I can control and measure pretty easily. I can also control and measure the magnetic fields fairly easily. Same thing goes with the cross-sectional area. But controlling the electric field is a little bit more challenging, and measuring it equally challenging. And so I want an expression that doesn't include this electric field. So I'm going to make use of my expression for potential difference because that is something that I can measure pretty easily. And I can plug in the potential difference divided by the distance between the two sides into my expression instead of the electric field. So I have E times A, and since it's in the denominator, I end up having delta V in the denominator and D in the numerator. Now there's one last thing that we can do to simplify this expression. And that's the fact that really my cross-sectional area can be expressed as that distance D times the thickness. Now we don't really have a set letter that we use for thickness here. I'm going to use Z as the letter for the thickness times delta V. By the way, your textbook uses the letter L for the thickness, but to me, L makes more sense for length, not thickness. I just chose the letter Z. We see that the two D's cancel out. And so now I'm left with an expression for the number of charge carriers per unit volume that is all in terms of things that I can pretty easily measure or control. I can pretty easily measure the current that I'm sending through. I can also relatively easily measure and control the magnetic field that this conductor is inside of. I can also easily measure the potential difference and the thickness of my conductor. So this is how experimentalists come up with the quantities of N that you can find in your textbook and that we've used in the past when studying drift velocity and current density. Now, just so you know, when it comes to the Hall effect, really we are focusing here on a stationary conductor with an outside current being sent through it. But the Hall effect, the idea of that separation of charge on either side of the conductor, also happens when you have a conductor that is moving through a magnetic field, as we'll see in our problem here. This problem is number 14 in your textbook. And in this problem, we have a metal strip. We're given the dimensions of that metal strip, and it's moving with a constant velocity through a magnetic field. We can see that through the diagram here. Similar to what we were talking about in the last slide, our magnetic field just pointed into the screen. We're told that there's a potential difference measured between X and Y, and we want to know the speed of my object. So again, let's think about this. If this is a conductor, there's free electrons located inside of that conductor. And my free electrons, they're going to be traveling with the speed V that is the exact same as the speed of the conductor. And it also tells me that it's moving with constant velocity. And constant velocity implies net force on not only my object, but on my surface is equal to 0. So the net force on my electron would be equal to 0. And in this case, that net force is a combination of a magnetic force, because it's in a magnetic field, and then there will also be an electric force set up by the fact that electrons are going to accumulate on one side of my conductor, setting up an electric field within that conductor. Since the net force is 0, I know that the magnetic force has equal in magnitude electric force. Or I could say that QVB sine theta is equal to Q times T. Being a Q on each side means I can cancel that out. And if I take a look at my diagram, I see that my velocity is perpendicular to my magnetic field. So the angle between them is 90, and the sine of 90 is equal to 1. So much like we've been doing in the past, we see that the velocity of my object can be found by saying the electric field divided by the magnetic field. Now, magnetic field is something that we're given in the problem. We're told that it's in a 1.20 millitesla field. However, electric field isn't something that we're given. Instead, we're told that there's a potential difference of 3.9 microvolts in the sides. Now, because we have charges accumulating as we do, let's think about this. If we have negative charges that are moving upward, they'd feel a force to the right. I have negative charges on the right-hand side here, which inherently makes my left-hand side positive because those negative charges had to come from somewhere. So I know that this potential difference comes from a relatively constant electric field. So just as we did before, the potential difference between the two sides can be expressed as that electric field times the distance between those two sides, which I'm going to call D. And so E in my equation here, I can plug in potential difference divided by D. And now I'm left with an equation for the velocity that includes three quantities that were given to me. A potential difference of 3.90 microvolts, or 3.90 times 10 to the negative 6 volts, divided by that distance between X and Y, otherwise known as the width, 0.85 centimeters, or 0.00850 meters. And then I multiply that by the magnetic field, which it tells me is 1.20 milliteslas, or 1.20 times 10 to the negative third teslas. I plug that all in my calculator, and I find that this object is moving with the speed of 0.382 meters per second. Again, even though really we are calculating the speed of the free electron, since that free electron is in my conductor, that is also the speed of the conductor. We'll do some more practice with what happens when we have conductors moving in electric fields, and we'll see some other interesting phenomena that happen because of it in class.